All right, guys. So right now we're going to go over enthalpy. And so we had just seen that when a chemical reaction occurs in a sealed container under conditions of constant volume, the energy evolves only as heat. However, when a chemical reaction occurs open to the atmosphere under conditions of constant pressure, such as the reaction occurring in an open beaker or the burning of natural gas on a stove, the energy can evolve as both heat and work. We have also seen that when the energy of the reaction is a measure of the total energy change, both heat and work, that occurs during the reaction. However, in many cases, we are interested only in the heat exchange, not the work done. For example, when we burn natural gas on the stove to cook food, we do not really care about how much work the combustion reaction does on the atmosphere by expanding against it. We just want to know how much heat is given off to cook the food. Under conditions of constant pressure, a thermodynamic quantity called enthalpy represents exactly this. So enthalpy of a system is the sum of the internal energy of the system and the product of pressure and volume. So H stands for enthalpy, and so it equals the energy of a system plus the pressure and volume. The enthalpy change, or delta H, of a reaction is the heat involved in a reaction at a constant pressure. So to find delta H, all you're trying to find is the heat of the reaction at a constant pressure. Usually delta H and delta E are similar in value. The difference is the largest for reactions that produce or use large quantities of gas. So when delta H is negative, heat is being released by the system. This is called an exothermic reaction. So if you remember me talking about delta E, when delta E is negative, that means heat is being released, it's being put off. Same with delta H. So when heat is being released, that means delta H is negative. When delta H is positive, heat is being absorbed by the system. So that's called an endothermic reaction. So when heat is being absorbed by a system, that means that delta H is positive. Now, you can actually see this in certain reactions. So in chemical heat packs, they contain iron fillings that are oxidized in an exothermic reaction. Your hands get warm because the released heat of the reaction is transferred to your hands. So an example of an exothermic reaction would be those chemical heat packs, so your hand warmers. Now, an example of an endothermic reaction is actually those cold packs that you use. So chemical cold packs contain ammonium nitrate that dissolves in water in an endothermic process. Your hands get cold because the pack is absorbing your heat. So what's happening is the pack, when the ammonium nitrate dissolves in water, it absorbs the heat around it and actually becomes cold. So it says identify each process as endothermic or exothermic to indicate the sign of delta H. So sweat evaporating from skin, water freezing in a freezer, or wood burning in a fire. So sweat evaporating from the skin cools the skin and is therefore endothermic with a positive delta H. The skin must supply the heat to the perspiration in order for it to continue to evaporate. Water freezing in a freezer releases heat and is therefore exothermic. So when you think of water freezing, you probably don't think of it as an exothermic because you think it's getting colder. Well, how is it getting colder? It's releasing that heat. And so that's going to have a negative delta H. The refrigeration system in the freezer must remove this heat for the water to continue to freeze. Now, wood burning in a fire releases heat and is therefore exothermic with a negative delta H. So in order for you to sweat, you have to absorb heat. That's why it's an endothermic reaction. Water freezing in a freezer is going to have to release heat. So if water is freezing, it's releasing that heat. Therefore, it's a negative delta H. And then wood burning, releasing heat, obviously. That's also going to be a negative delta H. So, molecular view of exothermic reactions. For an exothermic reaction, the surroundings temperature rises due to a release of thermal energy by the reaction. This extra thermal energy comes from the conversion of some of the chemical potential energy in the reactants into kinetic energy to form heat. So this is actually the conversion of the chemical potential energy into kinetic energy. So when a chemical system undergoes a change in enthalpy, where does the energy come from or go to? For example, we just saw that an exothermic reaction gives off thermal energy. What is the source of that energy? So where's that thermal energy coming from in an exothermic reaction? First, we know that the emitted thermal energy does not come from the original thermal energy of the system. Recall that the thermal energy of a system is the total kinetic energy of the atoms and molecules that compose that system. This kinetic energy cannot be the source of the energy given off in an exothermic reaction, because if the atoms and molecules that compose the system were to lose kinetic energy, their temperature would necessarily fall. The system would get colder. Think about it. When water freezes, those molecules are losing kinetic energy, and they're starting to move slower. Therefore, it's making it colder. So where do we get this heat? Yet we know that in exothermic reactions, the temperature of the system and the surrounding rises. So there must be some other source of energy. Recall also that the internal energy of the chemical system is the sum of its kinetic energy and its potential energy. This potential energy is the source in an exothermic chemical reaction. Under normal circumstances, chemical potential energy, or simply chemical energy, arises primarily from the electrostatic forces between the protons and the electrons that compose the atoms and the molecules within the system. In an exothermic reaction, some bonds break and new ones form, and the nuclei and electrons reorganize into an arrangement with lower potential energy. As molecules rearrange, their potential energy converts into thermal energy. So this rearranging of these molecules is what releases that heat. It's not the actual molecules themselves, it's their rearranging of their electrons that releases this potential energy into thermal energy. And so note that breaking bonds, when you're breaking a bond, it absorbs energy. It takes energy to break bonds. In an exothermic reaction, weak bonds break and stronger bonds form. It only takes a small amount of energy to break the weak bonds, and a greater amount is given off when the stronger bonds form, resulting in a net energy production. In an endothermic reaction, the opposite happens. Strong bonds break and weak ones form. The nuclei and electrons reorganize into arrangement with higher potential energy, absorbing the thermal energy in the process. So, it says, during the course of this reaction, existing bonds breaking and new ones are formed. Very, very important that when the bonds break, it requires energy to break bonds. What's happening is we get this thermal energy when they form the stronger bonds. So, the products of the reaction have less chemical potential energy than the reactants. The difference in energy is released as heat. Okay? So, endothermic. Let's talk about an endothermic reaction. In an endothermic reaction, the surroundings temperature drops due to an absorption of some of the thermal energy by the reaction. During the course of the reaction, existing bonds are broken and new ones are made. But remember, those new bonds are stronger. It takes energy to form those new bonds. The products of the reaction have more chemical potential energy than the reactants. To acquire this extra energy, some of the thermal energy of the surroundings is converted into chemical potential energy stored in the products. Okay, so very important. The reason why ammonium nitrate, when you're dissolved in water, is you're breaking strong bonds to form weak ones. Well, in order to do that, you have to absorb energy. That's why it gets cold. While on the other hand, when you're breaking iron and it's releasing heat, that's because these stronger bonds are forming, so it's releasing that thermal energy. These two slides are very good to study when you're looking at exothermic and endothermic reactions. So let's talk about enthalpy of a reaction. The enthalpy change in a chemical reaction is an extensive property. The more reactants you use, the larger the enthalpy change. Okay, so it depends on the amount of substance that you have. So the enthalpy change for a chemical reaction, and it's abbreviated delta H RXN, is also called the enthalpy of the reaction or heat of the reaction, and it depends on the amount of material undergoing. So we usually specify that the heat of the reaction in combination with the balanced chemical equation for that reaction. So since it depends on how much reactants you have, then it must depend on the molar ratios also. So by convention, we calculate the enthalpy change for a number of moles of reactants in the reaction as written. So here we have C3H8 plus 5O2 yields 3CO2 plus 4H2O. And our change in enthalpy is negative 244 kilojoules. What does that negative mean? It means that it's an exothermic reaction. So what this means is that 1 mole of C3H8 has negative 2,044 kilojoules, or if 5 moles of oxygen has negative 244 kilojoules. Okay, so let's look at an example of this. So an LP gas tank in a home barbecue contains 13.2 kilograms of propane. Calculate the heat in kilojoules associated with complete combustion of the propane tank. So you are given the mass of the propane and asked to find the heat involved in its combustion. So we're given the mass, we're asked to find the heat involved. So starting with kilograms of methane, we can convert to grams of methane, then use the molar mass of methane to convert to the number of moles. Next, use the stoichiometric relationship between moles of methane and kilojoules to determine the heat involved. This is a simple conversion equation. This is our conversion factor. We know that 1 mole of methane is going to have negative 2,044 kilojoules. So we can use that as a conversion factor. So kilograms to grams using 1,000 grams in a kilogram, grams to moles using methane's molar mass, and moles to kilojoules using that energy. Okay, so if you look here, that's exactly what they did. Again, it's just a simple conversion, and you use this 1 mole. Remember, it came from the balanced equation. So if you look back here, 1 mole of methane, that's where it came from. If there's 2 moles, then 2 moles would be at the bottom. And so the units are kilojoules are correct for energy. The answer is negative, as it should be for heat evolved by the reaction. All right, so measuring delta H. I'm going to stop here and start recording the next video.